Hello guys, welcome back to another episode of Let's Learn Computer Science. Today we're going to be covering operating systems, how they work, what they do, what their responsibilities are. It is a pretty big subject, so let's jump right into it. So first we're going to talk about the difference between system software and application software. Now an operating system is a type of system software. System software is a program that creates the environment in which creating and running application software is possible, and it usually interacts directly with the hardware. So this is how you can open up a task manager and see the temperature that your hardware is running at, for instance. Application software is written to address specific needs and solves a problem, where system software is usually not interacted with in that way. The OS manages computer resources and allows application software to access system resources. So I know, for instance, a web browser is able to grab the type of OS you're running, and that would be a part of your system resources. Continue on to the next slide. So these are the main functions of the operating system that we're going to cover today. The first one being memory management, which manages the RAM allocation, paging. RAM is a primary memory, and the hard disk is a secondary memory. So we're going to be talking about primary and secondary very often. The next function is process management, which coordinates processes running on the computer. It allocates CPU time and manages execution. And then CPU scheduling, which determines which process in memory is executed by the CPU at any given point. Now, process management and CPU scheduling kind of go hand in hand. All of this goes hand in hand, really, but CPU scheduling is very closely related to process management. Let's go on to the next slide here. So the first type of OS is going to be batch processing. This is not super popular anymore, but the first computers in around the 60s and 70s used batch processing, where it was a method of collecting jobs which needed similar resources into batches and then processed all at once, usually without any user interaction for large-scale and repetitive tasks. So back in the day, they would have an operator, which is a physical person, and programs were written on punch cards. And these operators would have to take these programs and feed them into a computer manually. And it would be doing one job at a time, and it would take a long time. So sometimes they would collect the jobs into batches and say, okay, this person from management and this person from HR, they both need access to similar resources, so I can combine those jobs into one to make this go a little quicker. Once we moved into a system of operating systems, that replaced the need of an actual operator, and it let the system software take control of a lot of those tasks. Let's go on to the next slide. So two other types of OSs is going to be a time OS and a real-time OS. Now, a time OS allocates time slices for each process for multitasking, and a real-time OS requires strict timing constraints, and it includes a minimum response time. So a time OS, the first one, is usually the one you're going to see most common in PCs now. This allows for running multiple processes at the same time, listening to music while you're downloading an application, while you're playing a video game. And a real-time OS is more popular in time-sensitive situations. So I think of maybe like a missile silo, some nuclear reactor, maybe certain business applications that require strict timing. That's going to be a real-time OS. So the batch operating system was a single tasking OS, and time OS was a multitasking OS. So this allows multiple processes to run at the same time versus only one process to run at a time. Time sharing is the idea that multiple users can interact with the same computer at the same time, and it creates this illusion that each person has exclusive access to the content that is on their page. But what's really happening is there's a mainframe with multiple dummy computers, and they're all connecting, sharing the resources from that mainframe, and it can do this by rapidly switching between the tasks. And then multi-programming is what allows multiple processes in memory at once. It is a reference to time slicing, like in the time OS, and it switches to a new task when waiting for an input or output. So we'll go a little bit more into process states, but there is a waiting state where a program's running, it's running, but then it's waiting for you to type in something. It's waiting for you to press enter. All right, so let's go on to the next slide here. So next we're going to tackle memory management. This is a pretty large topic, so we'll get through it quickly. Memory management is the idea that all programs and reference data is stored in RAM when executed. Otherwise, it's stored in your secondary memory on your hard disk. But when a program is being executed, it needs to be stored in the primary memory, the RAM. So your OS is going to determine, how am I going to grab stuff from the hard disk, or how am I going to determine what needs to be in RAM while a process is running? Let's jump into it. So RAM is a big continuous chunk of space divided into groups, and each chunk of memory has a corresponding memory address. Strategies are used to track where and how a program resides in memory and to convert logical addresses to physical addresses. Let's define logical and physical addresses now. So a logical address is when the variables in a program, when the variables in a program are compiled, they become logical addresses. Once that program is loaded into memory, all of the logical addresses are translated into physical addresses. And the mapping of a logical address to a physical address is called address binding. A physical address is another name for a memory address, and a logical address is another name for a virtual address. So you could imagine if you're familiar with C, with pointers, a pointer is pointing to a logical address once it's compiled. So let's go into memory management techniques. How is the OS actually determining how to manage the memory? There are three main ways. The first one being a single continuous memory management, where an entire app is loaded into one chunk of memory and only one program besides the OS can be processed. That's not very common. Next is the partition. There's two types of partitions. There's a fixed and a dynamic partition. Now, a fixed partition is where the RAM is divided into fixed size partitions, which is determined when the OS initially boots. Now, if you've ever installed a Windows server or even some Linux distros, you have the option to divide your partitions how you best see fit. And I'm pretty sure that's something you have the capability of doing in Windows 10, Windows 11. If you go to your file system, you can partition your drive differently. And for a dynamic partition, it is a partition that fits the needs of apps, and RAM is initialized as one large empty partition, so it's just the whole thing. Apps are then loaded only to use the space needed to accommodate the program. So it sees this large partition that says, okay, I only need this section, so I'll carve out this much, and this is mine now. If another process gets loaded, now it's left with the remainder, which is still the entire rest of the partition, and only carves out as much as it needs. And last, we have paged memory management, where RAM is divided into small size blocks called frames, and processes are also divided into similar sized chunks. The processes are called pages when they're divided, and the RAM is called frames when it's divided. When an app is executed, the pages are loaded into the unused frames in RAM, and to keep track of the unordered pages, the OS uses a page map table for each process in memory. So it subdivides them, it places them in random spots. They don't need to be continuous. If you have two processes running, it could be like, here's a page of process 1, here's another page of process 1, then process 2, then another page of process 1. So it subdivides it, and it can get messy. So they have this page map table in order to piece it all back together. Let's go on to the next slide here. Let's look at algorithms used in the partition memory management. The first one being first fit, where the program is allocated to the first partition big enough. It just starts at the first one and goes down, and it finds one that it can fit in and picks it. Best fit is it's going to look at all of them and choose the smallest one that it can fit in. And then worst fit, it chooses the largest partition that it can fit in, the one that would take up the most space. Now in a fixed partition, it prefers the first fit or the best fit. But a dynamic partition prefers the worst fit because it's just one large partition. Let's go on to the next slide here. All right, now we're going to dive deeper into paged memory management. This seems to be one of the more popular ways of managing memory in an OS now. In almost every Linux distro I've used, though, I've used a fixed partition technique. So in paged memory management, the idea of demand paging and swapping is introduced. Pages are brought into memory on demand. When a page is referenced, the OS sees if it's in memory already. If it is, then it completes the access. But if it isn't, then the page is brought in from secondary memory into any available frame. The act of bringing a page from secondary memory to primary memory, bringing it from the hard disk to the RAM, is called a page swap. Now, the idea of virtual memory and thrashing is also introduced. Virtual memory is where the operating system creates an illusion, leading a program to believe it has access to a large continuous block of memory, basically the entire memory of RAM, starting at address 0, even though only part of it is actually loaded into RAM at any given time. Now, it's important that the address starts at 0 because this helps simplify calculations. If it's always starting at 0, then I can just add my base of whatever it is, so that it keeps it in the back of its mind. With the virtual memory approach, the OS may have to constantly swap pages. Excessive page swapping is called thrashing, and it seriously hinders system performance. Let's go on to the next slide here. All right, now we're going to get into process management. So we're done with memory management. We went over the 3 types of memory management and then some of the algorithms that are present in managing the memory. And now we're on to how the OS manages processes. So a process is an instance of a program that is currently being executed. And process scheduling determines which processes should be executed by the CPU at any given time. A process moves to the running state only when the operating system's CPU scheduling algorithm says so. And here's a list of all the process states when you execute a process. Firstly, there's new. When you first execute the process, it's in the new state. Then it's ready, and ready is where it's waiting for the CPU's time, when it's waiting to be scheduled. Then running is when it is currently running by the CPU, when it has the CPU's attention and it's allowing it to do its business. Waiting is from the running state, so after it's ready, it moves into running. And then while it's running, it may have to wait for an input. It may have to wait for an event. And then lastly, there's terminated, when your process has stopped running, when it's done executing. Go on to the next slide. Let's talk about CPU scheduling. The act of determining which process is in the ready state should be moved to the running state. So this is the operating system deciding who gets the CPU's attention at any given moment. Now there's 2 schools of thought here. There's a non-preemptive and there's a preemptive. In the non-preemptive, decisions are made when a process switches from the running state to the waiting state or when a program terminates. So it's allowing each process to have its own time, get the same amount of love from the CPU. Now with preemptive, the currently running process state is decided by the OS at any time, which can forcibly stop a running process to switch to another one. So in non-preemptive, this might be something where when a process starts, it must finish. So what I think about is when you click 1 minute timer on a microwave, it's going to wait that entire minute and then be done. And then maybe it'll start another one, or maybe it'll do something else. But a preemptive might be an example like if you're using your phone, where you're listening to music and you're downloading something and you're scrolling on the internet. Now we're going to talk about a PCB, not the PCBs in mechatronics, but in computer science, it stands for Process Control Block. It is when the operating system stores data for an active process in a data frame called a PCB. It's created at the new process state and persists until the terminated process state. And a PCB stores a variety of information, including the value of the program counter, values of CPU registers, CPU scheduling info, and the amount of time the CPU has used so far, among many, many others. And lastly, we're going to talk about the CPU algorithms. How does the operating system decide which processes get the CPU's attention? Now here's just a few of them, but we have the first come, first serve method in which processes are executed in the order they arrive. So I click this, then I click this, then I click this. It's going to run the first one fully, then the second one, then the third one. This is a non-preemptive strategy. Next, we have the round robin, where processes get a small time slice in a rotating manner. This is preemptive because if I load 5 processes at once, it's going to say, give a little bit of time to this one, then give a little bit of time to this one, then this one, then this one, and just keep going, round robining. So each process is getting a little chunk of time, and that's usually what's happening when you're running many, many processes. The CPU's switching between each process, ignoring one for a minute to give this one some time, but it happens so fast that it seems seamless. And lastly, we have the shortest job next, which is another non-preemptive example. It is when the processes with the shortest execution time are executed first. This way, one process that takes a very small amount of time does not get lagged behind by a very large process. Now that concludes our overview of operating systems. There will be a lot more in-depth talk about operating system functions and file management in the future. Stay tuned because I have a lot more information for you. Thank you for watching. Goodbye.